Okay, The Evolutionary Biology of Aging by Ken and Michael. This is going to be the long version. That's going to take however long it needs to get through this 9 pages of notes that I took on this book. There's a lot here, but we'll go through it line by line, and then hopefully, I don't know, it's whatever. Okay, so in the introduction and stuff like that, in terms of basic, there's a couple quotes. In terms of basic science, we will argue that we now have foundations for understanding and mitigating aging in a manner comparable to the chemists. You can make this point once we've objectively altered the aging process. Chemists can objectively create chemicals. They can synthesize chemicals. You can use those chemicals. You can measure those chemicals. You can say, indeed, we have synthesized this weird thing that we came up with. We can't alter the human aging process at this point in time. So I don't think we're at the same level as chemists, even if you want to claim that. Let's see. When a breakthrough happens, the first section of such a book will be describing the breakthrough, not complaining about other people not understanding the breakthrough. You do a lot of berating of other scientists in this book, and I get it. We've all been there. Some of us are still there. So I get that. And there's a lot of berating to be done. There's a lot of justified berating. There's some unjustified berating in here. But, it's just like if you actually came up with something, you'd be talking about the thing that you built, not how everyone else sucks, right? So that's just a fundamental truth about the nature of discovery. Okay, so impact score on all these things, fine, whatever. I was kind of just like, what? Are you gonna assign a score to whatever? Okay, it's fine. And that was like these impact things right here. So Aristotle, aging is the accumulation of damage, but how does this explanation tolerate germline cells and their infinite capacity for division? Technically, he's not wrong, because in my opinion, aging is all three of the things. It's programmed, it's accumulation of damage, and it's antagonistic pleiotropy. All of them are true to various extents. You don't need to have one of them be more true than the other. I don't know why everyone's kind of upset. Not everyone, but certain people seem to be obsessed with like having the one true theory, or like the one true force, I guess. Sorry, I'm just sidetracking here. His lack of thought on this question set a precedent as widely sustained all gerontologists, blah, blah, blah. Yeah, so some guy thousands of years ago coming up with a wrong set of ideas. It didn't stop physics, and didn't stop medicine, it didn't stop chemistry, or, pyrotechnics or whatever. So people come up with terrible ideas all the time. It's not the presence of terrible ideas, it's the lack of good ideas. So yeah. Bacon, there's a chapter on Bacon that didn't really say much. I had a shower thought here. In fields where actual accomplishments are few, people are much more protective over ideas because the ideas are the only thing that exists. And so, like, if you were to talk to a physicist and try to argue against the concept of electricity, he would just laugh at you and be like if you came up to him and be like, electricity is not real, and I blah, blah, he'd be like, well, you're going to die within a couple weeks. Like that, they wouldn't bother trying to get into a heated argument over whether electricity is real, in the same way that this kind of whole thing is. So I actually feel like I shouldn't even be participating in this kind of an pseudo debate to this level, but whatever. I mean, I think this is kind of fun. So the specific selection hypothesis for blah, blah, blah first advocated was selection for the removal of older members of a population so they'd be detriment to young, blah, blah. The adaptive presupposition appears that were enough for aging population would be related with infirm older individuals. Okay. It's a weird notion because older members are only unfit because of aging. So if aging didn't exist, why would there be infirmity, right? That's, you know what I mean? Okay. Natural selection can eliminate aging whenever it bothers to do so. I agree with this 100%. In any case, Weissman's basic proposals, but the mechanism for how it does this is, I think, slightly different than how other people might think. Okay. Weissman again, single-celled organisms. Yeah, why were single-celled organisms not mentioned here? Which is kind of weird. But I guess you're supposed to, like, this is about multicellular creatures or something. I don't know. Oh yeah, and then this quote later: the effective immortality of the germline was always ignored as a puzzle facing mainstream gerontology. So let's see here, fruit fly density. There was a section about, yeah, I don't really know why that was included, but we'll just skip over that. Chapter 6, we're going down to, okay. This is the best point I think that you have in this book, is the fact that there needs to be more rigidity. It's definitely my weakest point at this, like my weakest aspect at this point is that I have concepts, I have theories, but having granular, falsifiable declarations where you say, here's what the pattern's supposed to look like, and then you can go out into the wild, measure the pattern, and see if it matches with the pattern that your theory suggests. That is actually like more of that's actual science. Coming up with concepts and putting logical pieces together, it's cool, and I think there's a lot of progress to be made there, but it's not like quite to the level of creating a theory, having an observation, seeing whether the observation fits with the theory. Is too much hand waving without math involved. So this is probably like the most salient point being made here with this book. But then I'll show you later. Okay, so oh, I don't like the fact that you reference the papers by their name and the date or the year. It's just like, I get that you have to go down and find it, but like we live in a digital world, right? It's not hard to just put the title of the paper there. So anyway, I just think it's a little bit better for creating context within how the sentence flows, but it's a minor point. It's whatever. Okay, page 24. Here we go. So when you put equations like this, it's so, in my opinion, this is me, it's so bad. I hate this. I hate when researchers dump an equation into the middle of a paper that's just the whole, like an integral followed by a string of letters and like some ridiculous thing, and they don't give you any examples. There's no like greater context. They just kind of like throw out what each variable is, and then they expect you to like do all the math yourself, and it's just like, can you just show how this is getting used? Can you show like what, because it's so annoying, right? I don't deal with exponentials, summations, integrals, derivative, all that kind of stuff on a daily basis. And to be honest, I've never used this in like normal reality life, right? So the familiarity is so low that I just look at this and it just feels like the person is just trying to use complexity like a bludgeon to like beat the reader over the head, like, look how smart I am, like that's the vibe that I'm getting. You're not actually, you don't use it, you don't show how this is actually getting like used to prove the point that you're trying to make. You're just like throwing it out there and being like, well, you're just an idiot if you don't understand this, like Okay. 28 again. Yeah, more of this. Oh yeah, the integral from 0 to infinity for e to the negative rx of L times x mx dx equals 1. Oh yeah, let me just formulate that in my head and just come up with a picture of what that means. Like, you know? Um, so anyway, bu- 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 what did I write down here? Everyone in academia who is afraid to look like an idiot, which is all of academia, nods along while only like a handful of people actually knows what this means. That's my interpretation of this. Thus, okay, we can go forward. Fisher laconically, blah blah blah. Valuing for fitness. Yeah. So again, the point about reproductive aging. This whole book assumes reproductive aging is occurring, and then that induces decline of natural selection, which then induces aging. But you don't even need that middle section. That's unimportant because the fact that reproductive aging is happening at all is aging. So what's causing that, right? That's the thing. And then the rest of it is just a product of reproductive aging. Okay. Let's see here. Yeah, I made a note, even though I'm having issues with the content of the book, I like the structure and how it's laid it out. It's how it laid out. This whole thing, title, standard paradigm, conceptual breakthrough, and then some sort of like conclusive statement. This is fantastic. This is great. The whole format of this thing is great. Okay, blah, 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 reproductive, aging, kind of, not really. So there's afterburner theory, or this is also like antagonistic pleiotropy, which is that there is a case to be made about predation and other forces that cause fitness differentials between early, like right when the organism reaches maturity, and then how it like there might be some math there, but it wouldn't be that if the organism has a natural tapering off of fecundity, that's aging. If it has a flat line of fecundity and then things happen from the environmental standpoint, that would be different. That would actually be the way what this book is attempting to explain is if there was no aging for reproductive fitness and it stayed a flat line, but for some reason the math forces caused a decline in reproduction that was not due to the innate loss of reproductive fitness that the organism experiences because of aging, then this whole theory starts to become very relevant. Like everything in this book becomes relevant. So that's that. Let's see here. Mutation accumulation, the other blah, 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 blah. Yeah, population genetic proposed for the evolution of aging. It's just damage accumulation and different wording. Yeah, I don't, an early example for the invocation of such cumulative physiological effects was the work of Lansing on rotifers. This was interesting. I knew of the effect, kind of like I understood the effect, the logic of it, but I never knew it was called the Lansing effect. So that's a term that I now know. Sociologically interesting that gerontologists were among the few who thought about physiology in Lamarckian rather than Darwinian terms. Yeah, yeah, that's that seems to happen. But again, like it's just kind of this like vibe that I'm getting this whole book. It's like, yes, you're smarter than everybody else. You are the smartest of them. And And I criticize this at the same time being a person who like egregiously does this themselves. So like I need to also not, you know, fall victim to this mindset, but it's there. Okay. Chapter 11, what was the 11 theory? What was this? Aging in a fish with continued adult growth. Um, that was, yeah, that was some kind of a, it was the trees. Oh yeah. The inverted fitness curve thing. Yeah. Um, that was kind of ridiculous, but it was, I mean, it's cool to include it. Okay. Chapter 12 was getting to some meat, mathematical derivation of forces of natural selection. It's just there's no examples. Like again, like you give all these summations and you know the math, the equations are there, but you don't actually show how this applies to like a real world example for anything. So um, that's it would be nice to see that. Um, Huntington's disease will impact the probabilities so late in adult life that the disease has little effect on Malthusian parameter. But if things didn't age, there would be no late life. So yeah, okay. Um, so the dark portion here is development. And then you've got this declining force of natural selection to zero. Um, what causes this, you know? And I'm just, I mean, I've said it like a million times already, but reproductive fitness changes in the organism. So there's change during development, and then there's change during this phase as well for all sorts of biomarkers and all sorts of things. But a lot of the germline programming is changing on its own. And so even the maximum fitness in an environment devoid of predators and whatever, you'd still get this decline because reproductive fitness is declining. Yeah. Okay. And so the point here was like the math, your math is applying to the thing you're trying to explain, not the explanation. How do I say this? A implies B implies C, but you're coming in and saying, oh, well, B implies Q and that implies C. And you're not explaining what Q is, really. You're just explaining what C is. And so that's not, I shouldn't have used the same letters as on this diagram. Now it's a little bit confusing, whatever. Going into the Hamilton paper, sorry. The molding of senescence by natural selection, consider 4 hypothetical genes in man, blah, 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 blah. This is for one particular year of life. Unity the first year, 15th, 30th, and 45th. Okay. Again, so this sentence right here, like if you didn't age, it wouldn't matter which of these, you know what I mean? Like, because for if you compare two non-aging individuals, the loss of 1,000 to 2,000 years of reproductive capacity versus taking out like 30 years of reproductive capacity, there's so little difference on a fitness scale that why would one be selected for over the other one? So, and what I mean by that is that if something lived for 2,000 years, and you've lost and you have a disease that hits at 15 years versus 45 years, then losing an extra 30 years on a timeline of thousands or hundreds of thousands of years, which would be an immortal organism, it wouldn't make any difference whatsoever for the math, for the reproductive math to work out. So I fail to see why this would make, like, you know what I mean? Okay. Hopefully you understand what I'm talking about here. Afflict and somatic mutation, disproven by system rates and versus theory, but can be disproven simply by understanding that single-celled organisms are functionally immortal. During the life of a single-celled organism, it should be accumulating mutations that it can't get rid of and then pass those on to the next generation because that's how DNA works. Oh yeah, so either single-celled organisms don't accumulate mutations, or it has to have a way of getting rid of mutations, which begs the question, why wouldn't somatic cells have the exact same ability, right? So whatever answer you have to come up with to explain germline aging or non-germline aging, how it clears damage, and this was actually brought up later on in the book as well. Whatever explanation you have for that, you have to explain why somatic cells are incapable of doing that when germ cells are capable of doing that. So that's a problem. Theory, blah, 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 chapter 14. Which one was that? 14. Oh, yeah, this is another thing where it's just like, if you just understand that single-celled life exists, then it can't be this thing. Or like this thing can't explain aging. Claim of a cultural shift, not really interesting, and it's hard to verify. That was the experimental designs to test evolutionary theories of aging. More Lansing effect stuff. You talked about Drosophila evolution, but you didn't mention diapause. And in fact, I don't think you mentioned diapause in the entire book. So that's concerning because it's like reproductive diapause in Drosophila is a very well characterized effect, has a lot to do with aging. It has a lot to do with the breeding stuff. It has a lot to do with being equivalent to Dower phase and C. elegans, which you talked about in this book, Dower phase. It's so prevalent. It's like so relevant to everything that's going on here, but you don't mention it, which is, I find it like just really like, like why? So that was suspect. Let's see here. Evolutionary experiments. Poorly designed equations, or poorly explained equations, lack of examples. Chapter 18. Oh yeah. So bunch of gene, dude, like what? What? Like, oh my God. Okay. Anyway. Oh yeah, and then I went to the Charlesworth paper because I was trying to figure out like what this all meant, and it's just pages and pages of integrals and summations. I like that there's a page on page 118 of the Charlesworth paper. There's experimental data comparing theory to observations. So that's like, okay, yeah, that feels like real science. All right. Blah, 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 blah. I think we've covered reproductive aging and its relevance here to that extent. He supposed that older outperform are the most selectively up to date. And thus would the older would drive to evolve towards relative inferior all right, the quote was, he supposed that the older individuals of a population are outperformed by the more selectively up-to-date younger individuals, and thus the older would evolve towards relative inferiority, but not absolute inviolability. This is, I think, the actual explanation, is that competition evolution drives aging, but not in the way that's described here. It's poorly described. There's another way of illustrating the whole thing, which I can go over at some time later. But competition can explain everything that's going on here. And it also ties into the force of natural selection and how the forces of natural selection, it just wraps everything up so well. So I think that this is like one of the more important concepts of this. There's a claim of a breakthrough here, but without real life example. I think this portion is just reiterating other parts of the book. Okay, if genetic variants with age-specific effects never arise in natural populations, then it's not possible for any of the evolutionary genetic mechanisms of evolution of aging to work. It's true, but it doesn't address the problem with the logic of this book. Okay, if mutation accumulation were a strong determinant of the evolution of aging, then they expected that such additive genetic variances would increase dramatically with adult age. Yeah. So just more refutation of mutation accumulation theory, which is, fine, whatever. I mean, how many times are you gonna dunk on these people? But it's fine, it's whatever. Okay, so in addition, if mechanisms of antagonistic pleiotropy, what was this? Then the postponement of aging by experimental evolution should be reproducibly associated with the reduction in some early life functional characters, trade-offs versus non-trade-offs. That's what this whole thing is. Yeah. So if mutation accumulation is the primary driver, there shouldn't be any trade-off mechanics, but we do see trade-off mechanics. So therefore, this is a strong piece of logic. Interest for the antagonistic pleiotropy hypothesis, reduced fecundity. A few chapters here we can kind of breeze over. C. elegans, some more math for antagonistic pleiotropy, some breeding issues with genetics, which I mean everyone kind of knows about, but if you don't, then I don't know. I'm sure new people don't know about this, so that's fine. Fissile organisms don't show mortality decline, while non-fissile ones do. Yes. The experiments show that aging isn't necessary, and the existence of single-cell organisms also shows this. So, yeah, I don't know why everyone's allergic to just being like, hey, single-cell organisms exist, so therefore a whole swath of this stuff can't be correct. Anyway. So, more antagonistic pleiotropy, blah, 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 blah. Genotype by environment is an allergic predictable result of this, saying that the aging-related characters of populations have not previously evolved in culture. Oh yeah, culture, evolution, okay. We can skip that. Observations that are paradoxical for accumulation of damaged components, but can be hand-waved away by up-down regulation of damage response mechanisms. Yeah, so people who say like accumulation of damage is the primary driver of aging, and then anytime that you give a counterexample, they can just be like, oh well, there's an upregulation of this damage control mechanism or downregulation or whatever. You can insert whatever like Deus ex machina element in there that you want, because the way that damage control works. So it's hard to, you're not going to pin them down on theory crafting. Anyway, moving on. Accelerated senescence and inbreeding. I don't know why I put this whole thing in here. Oh yeah, because semal parity. Any species that can swap between semal paris versus iterar paris. Yeah, I need to look this up. Are there any species that can swap between semal-paris versus iteroparis? Because then you can actually do a real experiment with semal parity. Without that, it's hard. Like you have to have like a clone of a species that is semal-paris versus non. And just I think that there's just too many structural differences between anything that went semal-paris and anything that didn't, for you to have like a real good experiment between the two. So yeah. I do think that you should have talked about it a little bit more, but whatever. Faster rates of aging. I mean, in general, in this book, because seminal parity kind of like destroys, like it's kind of counter to the whole concept of declining natural selection forces inducing age. It's very relevant, and I think that talking about how it interacts with your theory is a thing that should be done. Faster rates of aging should readily evolve by reverse selection for early reproduction in outbred populations. If you invert the experience from before, you should get the opposite results. So they bred longer. They took later reproductive aged organisms and bred them and tried to extend lifespan. Therefore, going the opposite direction should shorten lifespan. Basic demonstration of control over a variable, which is fantastic. So this is like just a strong piece of logic right there. 32, you go over reproductive male aging in the male Drosophila, much harder to measure, understandably so. How many genes determine aging? So there's a whole bunch, and this gets reiterated several times that there's a bunch of them, not just a couple. Fine, I don't understand it. I mean, I guess that's relevant for all the people that are really like diehard DNA is the answer to everything type of people, but okay, so whatever. So for some species he analyzed, senescence. Yeah. So, oh, I wrote this note. The purpose of this book is probably not to describe the actual math in detail, but I do think it would be useful, at least more useful than just slamming equations at my face. If you're gonna throw it out there, you might as well like have an example or something. This is, I've said it before. I'm not gonna repeat myself. Their estimates of this number suggested that so for 35, oh, it's just more about how there's lots of loci for gene control of aging. Sure, fine. First was proposed by Harrison and Archer. Of course, in aging, so for most of this book, mortality is considered the measure of aging. Later, you do go over at some point here how mortality and aging are disconnected from each other. But then you return back to it with the Gompertz stuff. So I don't like mortality is not I think I wrote it down. Let's just go through this. Okay, so caloric restriction, blah 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 blah. Yeah, caloric restriction is good. Stress resistance and longevity. Yep. So Gompertz mortality curve gets discussed. I heard that the results might have been refuted. So I'll have to look that up. That like, oh, it's actually, they thought it tapered off and it didn't really. So if it doesn't actually taper off, then this whole section is kind of, yeah. If it does taper off, well, there's a couple pieces that are like really weird here. Okay, so, oh, if aging can be evolved and de-evolved and it's purely a product of evolution, shouldn't it continue to extend indefinitely if later reproduction is selected for? The fact that you can't evolve it indefinitely means that there's other forces involved, right? That accumulation of damage is involved. Programmed aging is involved. It's not just antagonistic pleiotropy. So dietary restriction, reproductive trade-off, dower, yeah, so I like the fact that dower was mentioned, but there's no mention of reproductive diapause for Drosophila, which is weird. So development and aging in a comparison with longer-lived O populations. I mean, you've got so much data and evidence here. I'm not sure about data, but there's so much theoretical concepts here about fertility, fecundity, and aging. And yet, for some reason, it's just like completely like whoosh, that aging, that reproductive changes are aging. Like that is what aging is. So yeah. Mutation accumulation, more berating of other scientists and proclaiming how superior evolutionary theory of aging is. Okay. My mortality plateaus, nematode Drosophila comparison, still no mention of diapause. I wrote down Indian Methuselah genes covered there. Nematodes show antagonistic pleiotropy. Evolutionary theory hinges on the out. Yeah, so if that isn't the case, then anyway, this is an interesting. Okay, I'll get to that. So then more more assumptions about natural selection forces being dependent on reproductive changes and stuff like that. Okay. All right. When you look at data like this, okay, and it's forming a curve, right? You can't just draw a line through it and declare that it's a plateau when it keeps curving down below your thing, okay? Like, do you understand? Like, so this is still forming a curve, and then you just drew a line and then declared that it was not a curve. You can't do that. You just can't do that. Like, that's not a thing that you can do. So, you know, just, yeah, you can't do that. The vision that came up in my head was that scene from The Office with Michael Scott going, "I declare bankruptcy." It's just like, it's like, that's not how it works. This isn't how this stuff works, okay? So, anyway, all right. So attempting to explain, this is me saying I like how these fonts, this is sarcasm. Okay. Explain the fall for full longevity efficacy of breeding, higher and higher stress resistance, separation of aging and mortality. Yeah, so the fact that there's a ceiling that you can hit with natural, just using the force of natural selection, implies that the force of natural selection isn't the main driver here in the way that you've described it. I think that it is the main driver, but in a way that is a little bit more complicated. So, okay, separation of aging and mortality. Yes, here it is, chapter 51. So I read through this and I was looking for a phrase that would implies that anything that changes with age is part of aging. And I didn't see it, but like development, yeah. So that was, in my opinion, if something changes with age, that is what aging is. So change over time in a vacuum, in quotations, in the sense that if an organism was perfectly fit, it would still undergo changes, right? And you can delineate between development stage and post-development stage and all that kind of stuff. But if something just changes on its own in the organism over time, then that's what aging is. So development, aging, and late life are the three stages that you guys declared, which is, in other places, it's called development, maintenance, and decline. It's not a big deal. It's just, terminology. Finally, getting to single-celled fissile arguments. Yeah, so polar bacteria, which is interesting. That's gonna actually an interesting thing. So the what was covered here was at chapter 52 of 52. So rod bacteria can give rise, even though they're fissile, they can give rise to what, like the old pole and the new pole. The question there is, how does the bacteria segregate damage? How does it know how to segregate damage, right? Because there's a fluid innards, and so stuff is moving around, and then there's a copying of DNA and all that kind of stuff. How does it know to put all the new stuff into the new bacteria if it's the case that it actually does work the way that those people think that it works? How would it know how to segregate all the damage? And if it has a mechanism to segregate damage, then we can just use that mechanism on a human cell, and we've solved a massive problem, right? Because now you can create a fully new like stem cell in the stem cell creche using some mechanism, and then just get rid of the old stem cells, and now you've solved like a massive problem of aging. So this is not a problem, this is a solution in disguise. Yeah. Hey guys, talk about GWAS, finds many age-related genes, reiteration of the earlier chapters. Yeah, why wasn't all this stuff put together back to back instead of being spread out through the book? Fact that there's a lot of longevity genes and whatnot, it's fine, whatever. Transcriptome stuff, late life plateau stuff. Not enough centenarians for good science. Yeah, I'd agree with that. Specifically commonly assumed selective sweeps. Oh yeah, this like, I don't know if it like triggered me or something, but so this phrase selective sweeps was poorly described in your book. And then I looked up in the Burke 2012 paper, and they did not describe it well either. So then I had to dive through these references, and I think that like the main thing they talk about is the hitchhiking effect. So then I could finally understand, okay, so what's happening is that there's a gene that's useful, and then there's genes that are physically surrounding it. And if the gene that's really useful gets heavily selected for, genes that are physically right next to it also get selected for. So that causes this like signal, like it's sort of like a, it's like sort of like a weird signal where it's like hitchhiking genes that are just near really good genes get upregulated. And that there's some kind of a difference there between how mitotic organisms, how it happens in mitotic organisms versus non-mitotic organisms. And I don't quite agree, because like the loci of the homologous recombination locus in a mitotic or a meiotic, it's an organism that uses meiosis, the genes are swapped around, sure, but they're swapped around at very specific points. There's like very specific homologous recombination points. So you will get similar genes next to each other all the time. So that's the same effect will probably happen, even if it's not like as specific as a mitotic organism. You'll get a similar, I think you'll get a similar effect. So that was my understanding of this after reading that. Okay, and we're getting away from the point. The point here is the differentiation between sexual and asexual evolution, and I have a thing to explain the differentiation between those two things. I haven't seen anybody else explain it in that way before, so that's exciting for myself. Anyway, let's see here. Chapter 58, when does aging start? The classic argument of, does it start at the end of development or right at birth? More importantly, who cares? It doesn't even matter, because once you have data, like actual observational data, you won't even have an argument anymore. You'll just look at the data and it'll be blindingly obvious when it starts and to what extent it starts. And not only that, different systems might age at different points of time. So if there's a cascading effect where one system causes other systems to age later, you'll have a whole series of steps And so there won't be like a specific time when, aging occurs. And maybe it might be really complicated, but no matter how complicated it is, if you just observe the changes using diagnostic tools, you'll be able to put together, a picture of what's happening and know whether the interventions that you've come up with are doing anything or not. So I think that once you have data, none of that whole argument doesn't matter anymore. Oh, there's a big mistake here in chapter 58. Just because mortality rate is stable doesn't mean that they're not aging. Where is that? 56, 7, 8. This. Just because mortality rate is stable doesn't necessarily mean that they're not aging at that moment. It just means that there's no selection going, or there's no increased pressure of mortality going on at this stage. There could be changes happening here that you're not seeing emerge from mortality. So again, I just think that mortality and aging are not the same thing. And it's just a big piece. Okay, and then you go the heart and aging, sure, why not? Diet adaptation, more referencing of reproduction while treating it as not involved in aging in the final chapter. Yeah. So anyway, that's the big takeaway for me is like, actually, yeah, that was the main point, and then there's a whole bunch of other stuff. Do I think buying I'm not gonna go into that. I'll just say that yes, so I read the whole thing. These are my thoughts. Feel free to comment on whatever it is that you want to comment on or anything like that. I do think that the point being made of math being very important is like, I would agree with that heavily. Some other stuff I don't quite agree with your interpretation of certain natural selection concepts here, but anyway, that's that. I'm sure this video has been long enough, so I will end it there. Thanks for watching if you made it through to the end.